Welcome to today's paper reading. Today's paper is titled Visual Sketchpad, Sketching as a Visual Chain of Thought for Multimodal Language Models. This paper introduces Visual Sketchpad, a framework that enhances multimodal language models with visual sketching capabilities, published by Yushi and colleagues from the University of Washington and other institutions. The Sketchpad framework introduces a novel approach to multimodal language models, LMs, by providing them with a visual sketchpad and tools to draw on it. This allows the LMs to conduct planning and reasoning based on the visual artifacts they create. Unlike previous methods that rely on text-to-image models, Sketchpad enables LMs to draw with lines, boxes, and marks, which more closely mimics human sketching and better facilitates reasoning. Additionally, Sketchpad integrates specialist vision models, such as object detection and segmentation models, to enhance visual perception and reasoning capabilities. This framework has been tested on a variety of math and complex visual reasoning tasks, demonstrating significant performance improvements over base models without sketching. Sketches are a fundamental human activity, used for communication, ideation, and problem solving. Unlike written language, sketches directly convey visuospatial ideas. As multimodal language models have matured, they are now expected to solve tasks requiring intermediate sketches for reasoning. Visual Sketchpad is introduced as a framework that provides these models with the tools to generate intermediate sketches, enhancing reasoning in both mathematics and computer vision tasks. Figure 1 illustrates how Sketchpad enhances GPT-4's ability to reason over tasks by generating intermediate sketches. For instance, when tasked with proving that the angles of a triangle sum to 180 degrees, Sketchpad allows the model to draw necessary auxiliary lines that facilitate solving the geometry problem. Without Sketchpad, GPT-4o struggles to arrive at the correct answer, whereas with Sketchpad, GPT-4o successfully achieves the correct solution. This capability is showcased across various examples from 8, 51, 44, demonstrating the significant improvement Sketchpad brings to GPT-4's reasoning capabilities. In the related work section, the authors discuss three main areas: visual programming and tool use, visual prompting, and the concept of large language models, LMs, as agents. Regarding visual programming and tool use, recent advancements in LMs have shown the possibility of breaking down complex vision tasks into simpler steps, each solved using vision tools. Specifically, methods like VisProg and ViperGPT use LMs to generate Python code that sequentially invokes specialized vision tools. However, these methods follow a predefined plan, unlike Sketchpad, which allows for dynamic plan adjustments based on intermediate visual artifacts. Moving on to visual prompting, recent studies have demonstrated that multimodal models can be enhanced by adding visual prompts to natural images. For instance, the addition of labeled segmentation masks on images has been shown to improve GPT-4v's visual grounding ability. Sketchpad generalizes this approach, enabling LMs to decide the type of visual prompting to use during multimodal reasoning. Lastly, the concept of LMs as agents involves treating LMs as entities that can both reason and act. This idea has been applied across various domains, including software engineering, robotics, and vision. Sketchpad can also be seen as an agent that processes multimodal inputs and outputs, with the unique capability of creating visual artifacts to aid in reasoning, unlike previous LM agents that only generate text. The Visual Sketchpad framework is designed to enable multimodal language models to draw sketches as intermediate reasoning steps. This framework operates through an iterative interaction process, where the model generates thoughts, executes actions, and observes results to gather information needed to answer multimodal queries. The core of the sketching process involves code generation, which synthesizes programs to create visual sketches using specialist vision models and Python packages. This approach allows the model to manipulate both visual and textual content, enhancing its problem-solving capabilities by using visual sketches as aids in the reasoning process. Figure 2 illustrates the process of Sketchpad, a framework that enables multimodal language models to draw sketches as intermediate reasoning steps. The process begins with a multimodal query, which includes both visual and textual components. The Sketchpad agent then generates a sketching plan to address the query, referred to as the thought step. This plan is followed by the action step, where the agent synthesizes a program to create visual sketches. These sketches serve as a visual representation of the reasoning process. Finally, the observation step involves analyzing the resulting sketches to generate a final response to the query. This iterative process enhances the model's problem-solving capabilities by allowing it to plan and reason with the visual sketches it has drawn. This section of the paper evaluates the use of Sketchpad on 4 complex mathematical tasks: geometry, mathematical functions, graph algorithms, and game strategies. The authors demonstrate that incorporating sketching capabilities into language models, LMs, significantly enhances their performance on these tasks, achieving new state-of-the-art results. For instance, in geometry problems, drawing auxiliary lines helps in solving complex diagrams. In mathematical functions, Sketchpad allows models to visually sketch functions, improving efficiency. For graph algorithms, Sketchpad visualizes graph structures, aiding in direct reasoning. In game strategies, visual representations of chess boards improve analysis. The results show consistent performance improvements across all tasks, with an average improvement of 11.2% for GPT-4o and 23.4% for GPT-4 Turbo. Notably, Sketchpad achieves significant gains in graph algorithms and mathematical functions, highlighting its effectiveness in enhancing reasoning capabilities of multimodal language models. Table 1 presents the accuracy scores of Sketchpad on various tasks including geometry problems, graph algorithms, mathematical functions, and game strategies. The data shows significant performance improvements across all tasks when using Sketchpad, outperforming all baseline models. Notably, Sketchpad enhances GPT-4o's accuracy on the maximum flow problem by 41.3%, and GPT-4 Turbo achieves over 90% accuracy on mathematical functions. Additionally, there are observed gains of 3% to 10% on game strategies, indicating that visual representations of game boards can improve reasoning about strategies. These results underscore the effectiveness of Sketchpad in boosting the reasoning capabilities of multimodal language models. In this section, the authors experiment with Sketchpad on complex visual reasoning tasks. They utilize several specialist vision models wrapped into Python functions for sketching and image manipulation. These include detection using grounding Deno, segmentation using segmentAnything, and depth estimation using depthAnything. The experiments cover a range of tasks such as V*bench for small items, MMBP for revealing visual shortcomings, and Blink for tasks easy for humans but challenging for LMs. The results show that Sketchpad establishes new state-of-the-art results on all 7 tasks, with significant improvements in accuracy, particularly on V*bench and Blink tasks. Figure 3 presents examples of Sketchpad's application to various vision tasks, showcasing the actual outputs it generates. In stark contrast, the baseline GPT-4o model is unable to correctly answer these questions. It's important to note that for illustrative purposes, the NB marks in part A are different from the actual images used in the experiments. Table 2 presents the accuracy results of complex visual reasoning tasks, highlighting the enhancements brought by Sketchpad to both GPT-4 Turbo and GPT-4o models. The data shows that Sketchpad significantly boosts the performance of these models, setting new state-of-the-art levels across all tasks. Notably, GPT-4 Turbo sees an 18.5% accuracy increase on the V*bench task, while GPT-4o achieves a 12.1% improvement in relative depth tasks. Additionally, Sketchpad's effectiveness extends to multi-image tasks, where it provides a 7.5% accuracy gain. These results underscore Sketchpad's capability to enhance multimodal language models' performance in visual reasoning. Table 3 presents a comparison of Sketchpad with other augmentation frameworks for multimodal language models, LMs, on single-image tasks. The table highlights that Sketchpad is the only framework that consistently improves performance across all tasks. In contrast, the SAM framework enhances spatial reasoning but negatively impacts other tasks, even when combined with the original image. Visprog, on the other hand, underperforms compared to the base LM on all tasks, possibly due to errors in vision modules propagating through the program. This comparison underscores the effectiveness of Sketchpad in leveraging visual information to complement language processing in multimodal LMs. Figure 4 illustrates the percentage of times GPT-4o and GPT-4 Turbo utilize a visual module within the Sketchpad framework when tackling tasks such as v*operator bench, relative depth, spatial reasoning, and semantic correspondence. Key observations include GPT-4o's higher frequency of using visual modules compared to GPT-4 Turbo, the task-dependent nature of vision specialist usage, and GPT-4o's preference for segmentation modules over detection modules used by GPT-4 Turbo. The effectiveness of Sketchpad can be attributed to several key factors. Firstly, vision serves as a versatile and informational interface that complements language, particularly in conveying dense information such as depth and segmentation that are difficult to describe verbally. This aligns with the broader human development of visualization techniques that are direct, efficient, and informational. Secondly, Sketchpad allows multimodal language models, LMs, to plan and reason based on the intermediate visual artifacts they create, offering a flexibility and robustness not present in prior modular vision systems that follow predefined plans. This capability enables the LM to potentially identify and correct errors, such as those in object detection, which prior methods cannot do. Thirdly, the plans generated by multimodal LMs in Sketchpad are similar to human plans, suggesting a benefit from the underlying LMs having been pre-trained on data with similar reasoning patterns. A human study conducted on geometry and vision tasks supports this, showing high agreement between human and LM plans, with most errors attributed to vision specialists and simple visual question answering rather than planning. Table 4 presents the performance of open-source Olivier models on various math tasks. The inclusion of the Oracle Sketchpad, which uses visual artifacts from the last action of GPT-4o plus Sketchpad, consistently improves the model's performance on these tasks. This enhancement demonstrates the effectiveness of visual aids in boosting mathematical reasoning capabilities in multimodal language models. In this study, the authors introduce Visual Sketchpad, a framework designed to enhance multimodal language models by enabling them to generate intermediate sketches for reasoning tasks. This approach significantly improves performance in complex mathematical and visual reasoning tasks, setting new state-of-the-art results. However, the framework does require more computing resources compared to traditional language token outputs. The current work focuses on existing language models, but future research could explore integrating Sketchpad into the training process of models like Unified IO2 and Chameleon. Additionally, potential applications extend to robotics, where Sketchpad could aid in tasks such as object detection and navigation in crowded spaces. The author acknowledges the financial support received from the Allen Institute for Artificial Intelligence, Meta, and Apple. Additionally, the author expresses gratitude for the support from Amazon Science. The author also appreciates the help from individuals such as Zixian Ma, Weiqiu Ma, and Benlin Liu, as well as contributions from institutions like UW-NLP, Allen NLP, AI2 Prior, and UW-Raven. Thank you for watching.